Okay, for those of you who don't know me, my name is Gautam Satishchandran, and I was asked by Jonah to kind of give this like kind of what I was told it's kind of like an informal group meeting type update on what I've been doing and thinking about for at least the past year or so, and these slides here are slides or a expansion of some slides I presented at the APS meeting. So for those of you who are in that audience, I apologize. You'll kind of be seeing this talk twice, but I've certainly expanded quite a bit and brought in quite a bit more background. Okay, so the two talks that I'll be talking about, well, one, they're very much related to each other. One is memory effects and infrared divergences in asymptotically flat spacetimes. That's a work I've been doing with Bob Wald, and furthermore, in the end or second half of my talk, I'll be talking about how one should phrase these kinds of questions in situations when one has compact extra dimensions. That's with the eye towards string theory is the motivation, but it's really a classical question in the second half of my talk. So in the first part of my talk, I'll be just talking about 4 space-time dimensions and a lot of the preliminary ideas that I'll be talking about can be found in this paper that I've highlighted here. This paper looked at memory effects and these IR divergences in all space-time dimensions, but for the purposes of this talk, I'll just be talking about, again, 4 space-time dimensions for the first half of the talk. Okay, so just to kind of orient ourselves, we're going to be looking at asymptotically flat space-times. Why should one do so? Well, there's lots of nice, interesting reasons to consider asymptotically flat space-times when we're modeling things like binary black hole mergers or things that, in particular, that LIGO would detect. We'd like to model them as two events or mergers that are occurring deep within the space-time, and asymptotically, in particular in asymptotically null directions, we're going to characterize these space-times by requiring that the metric, this G, asymptotically approach the Minkowski metric in these null directions. So R here is the parameter of a null geodesic, and we're just requiring that the metric approach this Minkowski metric at time at null infinity. Why should we do so? Well, of course, this is the direction in which gravitational radiation flows to, and in order to keep track of gravitational radiation and track interesting quantities such as the mass or charge of the space-time, or sorry, momentum, charges will come later, momentum of the space-time, we'll want to compute these quantities in a region where we can keep track of all the radiation that is emitted in the space-time. So it'll be useful to also consider this incoming null cone. So to a relativist, this would be called null infinity, but we don't really need such like kind of abstract mathematical notation. This is really just some large incoming null cone whose cross sections are asymptotically large spheres, and so the topology of this cone is R cross the 2 sphere. And it's useful to invent some parameter here, U, which you can just construct asymptotically by this, taking the global inertial time that you get from the metric being asymptotically flat and subtracting R. So this is just the retarded time asymptotically. And so retarded time runs up and down this cone. And again, these cross sections are large spheres. So the reason one would, the reason why one would want to be interested in these spacetimes, again, is just due to the fact that this kind of cone here captures all the gravitational radiation that is emitted in the spacetime. And of course, I'm not the first person to investigate such spacetimes. This investigation was first done by Bondi, Messner, and Sachs in the 1970s and has been an area of active research since then. One, because of the direct detection of gravitational radiation by LIGO, but furthermore, there have been recent theoretical interests in these asymptotically flat spacetimes. the triangle, or this Strominger infrared triangle, is meant to evoke the idea here that these three ideas that I've written down are actually, which are all features of asymptotically flat spacetimes, and we'll see very deep features of asymptotically flat spacetimes are connected in some way. So the memory effect is a property of classical gravitational radiation. It's something that LIGO or LISA will detect in the next 10 years or so, with finer and finer resolution in their measurements at low frequencies. And we'll see. I'll be defining this object in a lot more detail shortly. The asymptotic symmetries of an asymptotically flat space-time is intimately connected to the memory effect. We'll see in a moment. And asymptotic symmetries are just the emergent symmetries that one gets when one, requires that the metric be asymptotically Minkowski. So you can imagine that there are some symmetries. There are no exact symmetries in the bulk, but there are asymptotic symmetries as I approach the Minkowski metric. And as we'll see, and this is the subject of a majority of my talk, the infrared divergences in quantum gravity or in quantum field theory are also intimately tied to this memory effect. So this is the Strominger infrared triangle, as I mentioned, and it's meant to evoke that these ideas are intimately connected. And if you were wondering as to exactly what do these links mean and do they hold in higher non-compact space-time dimensions, I would urge you to go to the paper I highlighted in the first slide of my talk, where we really analyze this rigorously in all non-compact space-time dimensions. So the reasons for Strominger highlighting these connections were, one, particularly to quote unquote solve the black hole information paradox. He was interested in the fact that these asymptotic symmetries are, we'll see, as an infinite dimensional group, and thereby could or do constrain scattering and the formation of black holes or any classical properties of space-time. And these infrared divergences really, as we'll see, the story is not so complete in this sector here, but he conjectured that the low frequency behavior of the theory could be entangled with the high frequency modes, and this entanglement could store information. So that was the idea. So we'll be talking much more deeply about these infrared divergences, and I won't make any comments as to whether or not this solves the black hole information paradox or anything, but as we'll see that these three vertices of the triangle are interesting in their own right. Okay, so this is the outline of my talk. The first half of my talk is just, again, talking about asymptotically flat spacetimes in 4 spacetime dimensions. And then if I have some time at the end, I'll be talking about the extension when one wants to add compact extra dimensions. Okay, so just to get us all oriented, we'll be talking about just classical gravity first. And we'll really define the memory effect and the associated asymptotic symmetries. Then we'll turn to quantum gravity, where we'll analyze the problem by looking at a toy model of linearized quantum gravity with a classical source. And then we'll turn to full quantum gravity. And we'll see that memory is just, or infrared divergences is a ubiquitous feature of any theory of quantum gravity. And this will call into question what the Hilbert space structure of quantum gravity is at low frequencies. And we'll make some concrete steps towards that direction. Okay, so let's get started. So just to get everyone on the same page, I know the audience is probably quite mixed, and I'm definitely not talking to a room full of relativists, otherwise I would kind of gloss over these more relativity-minded details, but let's just get everyone on the same page with classical gravity. So what is the memory effect? Well, the memory effect is the permanent relative separation of a system of test particles brought about by the passage of a burst of gravitational radiation. So we can visualize that in the following way. If I, put some test particles on a ring, and I allow some gravitational radiation to pass through my, or from your perspective, your computer screen, then these test particles will oscillate relative to each other, and they will generically settle down. And if the memory effect is non-vanishing, the test particles will settle down to positions that are not equivalent to their original positions. And this is an instance of the gravitational memory effect. Okay, so this is in principle detectable by LIGO or LISA, and it's useful to understand the link to asymptotic symmetries to consider, well, first we need to consider how does one actually calculate this effect, where we do so by integrating the geodesic deviation equation. So if you don't know what the geodesic deviation equation is, that's okay. You can just skip to the punchline here, where we find that the relative separation of the test particles is just given by some linear map delta on the initial displacement. So this almost has no content because we need to still tell you what delta is, but really the key idea here is that this tensor delta is the real quantity that we want to keep track of. It measures the displacements of my test particles, and we call it the memory tensor. So let's look at this in a more global way, where what I'm going to do is, let's go back and take this ring of test particles and localize it to a sphere on my null cone. So this cross section is an asymptotic sphere of my null cone. And since I have to go down in dimension to draw this cross section, I can only really represent my array of test particles by just two neighboring points. But you should really imagine that these are an array of test particles on the sphere. And since we have this kind of global perspective now, let's populate the whole sphere with these particles and look let's examine what the memory effect does to this full array of test particles on the asymptotic sphere. So the radiation is implicit in this diagram. It's incoming or outgoing to future null infinity. And generically, if there's a non-vanishing memory effect, the test particles will be relatively displaced relative to their initial position. But now it's very clear they suffer some angular displacement is really the key point. And if we measure the distance between these two particles, between early and late times, they will not be equivalent for any pair of particles that we see on the asymptotic sphere. So generically, it'll take this kind of array, nice array, and then wiggle them into asymptotically late times. Okay, so this global perspective is useful for understanding the relationship to asymptotic symmetries. First, what is an asymptotic symmetry? Well, it's just a group of diffeomorphisms that are non-vanishing at null infinity, this null surface, and quote unquote preserves the structure of null infinity. What do I mean by that? Well, it's, for example, I could take this asymptotic cut that I made and do an asymptotic rotation. So just apply a rotation to this cut. That's an example of a diffeomorphism that preserves this structure and therefore is an asymptotic symmetry. So the question is, what are the full group of transformations that I could do to this cone? Okay, so Bondi, Mesner, and Sachs were the first to do this in the 1970s, and they guessed that the asymptotic symmetry group would be the asymptotic symmetry group of the flat metric, which is the Poincare group, which is given by the Lorentz group semi-direct product with a translation. So the translations are the time translations, where retarded time goes to retarded time plus a constant, otherwise known as an L equals 0 spherical harmonic, or a spatial translation. Actually, in this way of looking at things, turns out to be retarded time goes to retarded time plus an L equals 1 spherical harmonic, which has a degeneracy of 3, which is exactly the 3 spatial translations. Okay, what they found, or sorry, let's, there's this, sorry, I forgot that I added this. This has some clear-cut motivation, while the time translations and the space translations correspond to energy and momentum asymptotically at null infinity. And the change in these quantities between early and late times correspond to gravitational radiation loss due to your, for example, binary merger that you're considering. Okay, so what did they actually find? Well, they found that the group was the BMS group. So this is a finite dimensional group, the Poincare group, but the BMS group is an infinite dimensional group. And where do these extra generators come from? They come from the super translations, where now a super translation is u goes to u plus any arbitrary function of angles. If it's L equals 0 or L equals 1, it's a time or space translation. But if it's a higher harmonic function, then it is a super, or it is this infinite dimensional generalization. And the structure of null infinity does not tell us to get rid of these transformations. So the question really is, what is the observable associated to this higher harmonic? And the way we can understand this is just consider the action of a supertranslation at null infinity. So if we do so, you can see the following. So if I take a cut at null infinity, what does a supertranslation do? Well, it instructs me to move forward in time by an angle-dependent amount. Depending on where I am on the sphere, I move forward in time by a different amount. Well, this precisely brings me back to this wiggly cut that we saw earlier. And if this figure is reminiscent to you at all, it's because you saw it to, I just removed the points of my test particles, and it's exactly the same. So the motion of my test particles at null infinity are the motions, or are given by a asymptotic supertranslation from early to late times. Okay, so memory is intimately linked to asymptotic symmetries. There's a formula that kind of encapsulates this, so it's not just all pictures. The memory tensor is given by, well, this D operator is just an angular derivative operator on the asymptotic sphere. Q is the metric on the sphere, and this T here is a supertranslation function. Okay, so so memory is intimately linked to this supertranslation function, and it's useful to kind of unpack what this object really means to determine what memory really depends on. So like, how do we write this function in terms of observables in the space-time? So if I'm categorizing the complexity of equations in my talk, this is maybe one of the more complicated ones, and it's really not so essential to unpack every step of this object. These are just inverse elliptic operators on the sphere. So these are, for every eigenvalue, these are just numbers, we can ignore them. This delta P and the F are really the key players here. P is this, not so illuminating asymptotic, Weil tensor component, which is just a component of the curvature. But if you, for scattering in particular, P turns out to be, or delta P turns out to be the change in the angular distribution of the incoming and outgoing form momentum. So really what it's saying is that if I have, for a binary merger, I have a net quadrupole at early times, and then at late times, I have a monopole, for example, then the change in the angular distribution due to this, change from quadrupole to monopole will give a non-zero delta P. So any non-trivial scattering will give a non-zero delta P. And then the second term is very interesting. It's just the total flux of energy out to null infinity. But we're restricting to higher harmonics. So as long as the flux of energy is not, a pure L equals 0 or pure L equals 1, it has these higher harmonics, as it would generically will, then you will produce a term, this blue term here. So in particular, it's the flux of stress energy to null infinity, as well as the gravitational radiation energy that makes it out to null infinity. This is this NAB squared term. I won't go into any more detail in this part of the talk about this, but it will be a kind of a central player in the second part. So if we make it that far, then we'll talk about this in more detail. So I think I stressed this already, but for classical scattering, the memory effect vanishes if and only if the scattering is trivial. Okay, so now we turn to infrared divergences, and we will study infrared divergences by first looking at this toy example. We're going to consider linearized quantum gravity with a classical source. So take a stress energy tensor, smooth stress energy tensor, multiplied by the identity operator. And technically, we're going to construct this Hilbert space here. So if this is also not so illuminating to you, this is just the usual Hilbert space norm. So we're going to take our space of gravitons to be the space of test tensors psi with positive frequency with respect to time, and have finite norm with respect to this inner product. This inner product really just comes from the symplectic product from two solutions to the Einstein's equation restricted to null infinity. And it's the same that one gets. It's very similar to the one that one gets from the Klein-Gordon norm and what have you. So I can expand on this in more detail, but this is just the standard symplectic product restricted to scribe. Okay, So what is the punchline? Well, given this source, this smooth stress energy tensor multiplied by the identity operator, we can generically write down the out state. It's just a coherent state associated to this retarded metric. And this retarded metric is going to be the retarded metric associated to this classical stress energy T. So the reason I've written formally here is because psi only defines the state in the out Fock space if and only if this retarded metric has finite norm with respect to this inner product. So when is that the case? Well, if the memory tensor is non-vanishing, then the change in the retarded metric from early to late times will not be zero. And at low frequencies, the retarded metric will diverge like 1 over the frequency. This is just the Fourier transform of a step function, like behavior. So the norm squared will diverge logarithmically at low frequencies whenever the memory tensor is non-vanishing. Okay, so we have the following kind of concrete statements that we've learned from this toy example. Psi only defines an element of the out Fock space if and only if the memory tensor vanishes. Conversely, if the memory tensor is non-vanishing, then psi can be represented as an element of a different Hilbert space, F tilde. However, F tilde is not unitarily equivalent to the out Fock space. Every element of F tilde diverges in the norm of the out Fock space, so they cannot be unitarily equivalent to each other. Okay, and finally, just to make contact with what some people might know in the high frequency, in the high energy community, choosing a frequency cutoff, omega naught, the out state can be factorized into a hard and soft part. And this factorization is given here, where the hard part is the part of the state with frequency greater than omega naught, and the soft part is part of the state with frequency less than omega naught. This factorization is equivalent to what is known as the Weinberg soft photon or graviton theorem, where the S matrix amplitudes factorize into low frequency and high frequency parts. These are equivalent.
This is really like an honest tensor product between.
This is an honest tensor product, but recall this is only for this out state where we've for some classical current. If we have, so I'll talk about actual quantum matter, where now for a generic out state, given in one sector of the memory tensor, you'll get this factorization, but you can have superpositions of memories, and then you generically an out state will not have this factorization property.
Okay.
Right, so we'll talk about that in a second. Good. So now let's turn to full quantum gravity, and I'm sure most of you should be perking up your heads at the moment. What do I mean by quantum gravity? Well, as was shown to us by Ashtekar in '81, one can talk about the kinematic structure, basically. The out Hilbert space is well defined at null infinity, even if the quantum gravity theory, the actual dynamical theory, has not been defined at the interior of the spacetime. So we can quantize the radiative modes at null infinity, even if we haven't defined the interior theory. Okay, so that's good enough to talk about what can happen in quantum gravity. I'm really only talking about kinematic structure for this part of the talk anyway. So considering a scattering situation where we have some non-interacting ingoing and outgoing hard particles at early and late times, then it's reasonable to consider that the soft content, this low frequency behavior, just comes from this incoming and outgoing hard particles, which at early and late times are not interacting and are effectively classical. So the considerations of the previous slide seem to imply that it's plausible to believe that we'll get an IR divergence in the full theory of quantum gravity as well. Okay, but there's one major difference. When one considers quantum matter, there's non-vanishing amplitudes for various different hard out states. And there should be non-vanishing amplitudes for different non-zero memory tensors. So as opposed to this classical current or classical stress energy example, in this full quantum matter story, we need to include all of the out Fock spaces. For all F deltas for all possible memories, where all of these F deltas are unitarily inequivalent to each other. Okay, so at this point, you should be concerned and maybe confused as to why this hasn't been brought up before. I'm posing a question that seems genuinely new, and really this question doesn't just exist in quantum gravity, it exists in quantum field theory, in particular in QED. And at this point, it's just useful to just take a step back and let's see what people do in QED to deal with this problem. So IR divergences in quantum gravity have direct analogs to QED, where there's a corresponding electromagnetic memory effect. And so memory is in one-to-one correspondence with infrared divergences. I hope that's clear at this point. Okay, so there have been various approaches to dealing with infrared divergences in QED. Well, one approach is to just simply choose some infrared cutoff and then just integrate out all the low frequency behavior. I hope it is clear now that this procedure necessarily removes the memory effect from the set of observables in the quantum theory. Furthermore, one can, a more, slightly more refined approach is to, by Fadeev and Kulish, is to dress these asymptotic states with non-unique, I should stress, finely tuned low frequency radiation. And this radiation is just such that the memory effect is killed for both the in and the out states. Of course, this kills the infrared divergences, but really the character of these two approaches here is that the low frequency behavior is unphysical completely, and one should just, change the structure of the theory at low frequencies such that, we remove some set of observables or, add some finely tuned radiation so that we can never talk about such observables to begin with. So our view of the infrared divergences are in QED and in quantum gravity is that they correspond to a classical observable, the memory effect. A more correct approach would be to construct a Hilbert space that incorporates all such IR effects. So I should also stress that there are particular, more subtle questions that one could ask in which you would get different answers given these two approaches. For example, if I ask questions like, how is the low frequency behavior of the theory entangled with the high frequency modes? These, if you decided to choose either one of these two approaches, you would get completely different answers. And questions like unitarity of the outstate that people at Strominger et al. Want to consider when where you really do need to keep track of these low frequency modes, then the real question is, how does one put together these low frequency modes in such a way that doesn't ad hocly, just change the theory at low frequencies? Okay, so how does one do that? Well, I've posed the question, but now we need to kind of put these all of these out Fock spaces together, and there's an uncountably infinite number of them for all possible memories. Okay, so the key insight here is that memory, as I kind of mentioned in the classical part of this discussion, is correlated with the momenta of the incoming and outgoing hard particles. And in a theory without an infrared cutoff, the in and out states cannot have definite momenta, and therefore the in and out states cannot have definite memory. This is a useful insight because therefore one can't take a simple direct sum over all of these out Fock spaces, over all the deltas. The direct sum would correspond to states of definite memory, and it would, it's easy to see, would be a non-separable space anyway. Rather, one must take the separable direct integral, which allows for distributions in memory. So I don't have time to get to the construction of a direct integral. This is the symbol that one writes down when one wants to talk about a direct integral. We're integrating these Fock spaces with respect to some choice of measure, d mu delta, on the space of memories. Okay, so I mean, the key point here is that in order to construct a direct integral, one must supply a measure on the space of memories, and the states are just square measurable functions of memory with respect to some choice of measure, this d mu delta. And so to avoid the idea that these d mu delta is just some mathematical artifact, it has a direct physical implication. So out states with different memories, peaked with different memories, if they have non-vanishing overlap under this integral, they'll be entangled with each other. Their low frequency modes will be entangled with each other. And this degree of entanglement is directly determined by this measure. For example, if this measure was just the point measure on the integers, that would correspond to the direct sum, and then two states of different memories would be orthogonal to each other. But now that we're allowing distributions of memory, we're allowing two states with peaked at different memories to have some non-vanishing overlap, and therefore have non-trivial entanglement. Okay, so this is the kind of the physical picture here. So now what I'll want to do is just, let's just try to prescribe some Hilbert space, thereby prescribing some measure on the space of memories. And we're going to see that this is just not so trivial. So if I'm categorizing my slides here, this is certainly my most technical slide. So what I'm going to do is just kind of give you give you a flavor for what's going on, and kind of not get too into the weeds as to the mathematical details. Though all the mathematical details will be presented, but I'll just be saying in words what I mean. So we want to provide a consistent scattering theory, and in order to do so, we want the translations and the Lorentz transformations to be unitarily implementable. This corresponds to some constraints on the measure. This first constraint I won't be really unpacking unless they're asked a question about, but it is a constraint on the measure that implies that the translations are unitarily implementable. And I've noted here in this point too that if the measure is Lorentz invariant, for example, then of course the Lorentz transformations are unitarily implementable. Okay, so why could we think that we could even do this for a particular case of even Gaussian measures? So I won't again explain what a Gaussian measure really is, but I'll give you some, just a few details. The Gaussian measures are uniquely determined by some choice of inner product on the space of memories. And we prove that there exists a unique Lorentz invariant inner product on the space of memories. It's this L2 integral over the asymptotic sphere on the memories. So point 2 could very well be implemented if we just chose our Gaussian measures to be determined by this inner product. Okay, but the final result here is, well, I'll just say in words what I mean. Well, we showed that the Lorentz transformation, if you can implement the Lorentz transformations, one cannot implement the translations. And it goes vice versa. If we can implement the translations, we show that one cannot implement the Lorentz transformation. So they're, for Gaussian measures, mutually exclusive to implement both the Lorentz transformations and the translations, and therefore we prove that all Gaussian measures are incompatible with a consistent scattering theory. Okay, so where can we be headed, and where can we go from here? Well, let's just look back and see where we've been first. So IR divergences are physical. I hope we all can agree on that now, and they correspond to a classical observable, which is the memory effect. One must include these effects into what we argue is a direct integral space, which requires some choice of measure, this mu delta that I've written here. And we've seen that a naive prescription of such a Hilbert space fails to provide a consistent scattering theory. Okay, so where can we go? Well, the fundamental question is, what is the appropriate measure for the in and out states, which yields a consistent scattering theory that allows me to talk about, low frequency radiation on the same footing as all other, kinds of radiation. And it's useful to rephrase this question and in the, following way. Well, I hope it's clear that this is equivalent to just how the hard and soft sectors are really entangled with each other. The measure really comes into understanding this entanglement structure between these hard and soft sectors. And the answer to this question is a measurable property of the quantum field. And therefore, measuring the entanglement should provide some insight into the direct integral representation of the out states, and then yield a Hilbert space structure for quantum gravity and quantum field theory that includes all infrared effects. Okay, so I think at this point, before I move on to the second part of the talk or whatever, I maybe should just take any questions. I know Jonah asked one, but if anyone else has some relevant questions or whatever on this part, since they're kind of disjoint, I could field them now if anyone wants, or I can field them at the end.
If one was cynical,
yeah,
about the physicality
please be cynical.
Yeah. So wouldn't one say, oh, in reality, any physical observer can never really reach SCRI. It can never be at infinity. You have to be at some long distance away, but finite distance, and that's an equal cutoff. So
Okay, go ahead.
Yeah. So any effect that really requires you to go out actually to asymptotic infinity isn't actually measurable.
So we're defining, the only reason I go to infinity is to define radiation. Obviously this is just truly radiation is just the decoupling limit from Coulomb fields, right? So in the sense that time-dependent stuff that gets out to infinity, I can define as radiation. So really going out to SCRI is not so important, but you did mention that I could, any detector really would have an infrared cutoff tied to them, and therefore you would think that you would not be sensitive to the low frequency behavior of the theory, but there are kind of subtle questions that one could ask. For example, how much information is lost when I make a measurement of the quantum field with some infrared cutoff? That depends on the Hilbert space structure of the fundamental theory. That doesn't just depend on the high frequency behavior. And that question can't be answered unless one has a real prescription for how the scattering, what the Hilbert space structure of the theory is.
Mm-hmm. Good.
Any other questions?
Sorry, I have to unmute myself. So I think one other question. So if I'm understanding correctly, you say that hypothetically, if you could do these entanglement measurements, then you would be able to show that there is some measure mu delta that exists that you could kind of extract from experiments. But you've proven that that measure mu delta which exists cannot be, you can't implement Lorentz translations, or it can't be Gaussian. So is the statement that one of those three assumptions must fail for whatever this true measure is? And if so, which one do you think fails for the real answer, basically?
What fails is that it's Gaussian. I believe that any consistent scattering theory would unitarily implement the Poincare group at least, or the BMS group really. So I under that belief, and I don't have any reason to not believe that, then the failure is just on the Gaussian measures themselves. So this is just some infinite dimensional measure that was lying around, and we just decided let's prove whether or not it's implementable or not, and I proved that it is not.
Okay, so the definition of Gaussian was roughly just that it's something that you could write in terms of some inner product. So there's a measure that's not descending from an inner product, you're saying?
That's right. Oh, well, no, definition of Gaussian is more restrictive than just the existence of an inner product, but one can uniquely construct a Gaussian measure from an inner product. But that doesn't mean that all measures created from inner products will fail. That's not the takeaway. It's just
okay. So there could exist an inner product, and you're just saying there is an inner product. You can construct from that inner product the Gaussian measure, but that is not the measure that would actually be measured in experiment.
Exactly. That's exactly right. Yeah.
Okay. Good.
Okay, so I can take more questions at the end too. So maybe I'll just keep going if that's okay with everyone, and then we can talk about everything. So good. So I don't know how to move forward. Okay, in contrast to the previous talk, which was mostly about quantum gravity, I titled this part of the talk "Isolated Systems with Compact Extra Dimensions." The eye is towards string theory, which of course is a theory with compact extra dimensions. But really, we're trying to just understand the classical structure of such spacetimes. Okay, so I'll be trying to characterize what we mean by an isolated system in this case. We'll look at the asymptotic symmetries, and then we'll determine the, how does radiation look like in these spacetimes. Okay, so previous analysis, the previous analysis that I just showed in 4D asymptotically flat spacetimes discusses only the kinematic structure of quantum gravity. And in order to discuss the dynamical structure of the theory, one must make contact with an actual theory of quantum gravity, in the bulk of the space-time. So For example, one could choose string theory as a, such a viable example, and this association is not so clear because this classical structure requires this 4D asymptotically flat behavior, but compact extra dimensions are a robust prediction of string theory, and at the classical level, a complete analysis of radiating spacetimes with compact extra dimensions has just never been done. So what we're going to do is just tackle this question that we posed in the bullet point, which is really what is the complete construction of these spacetimes to a sufficient degree that we can talk about nonlinear, non-perturbative radiation. Okay, so to get a handle on what has been done, for linear perturbations off of any compact spacetime, these linear perturbations effectively look like an Einstein-Maxwell. This is a dilaton. This is just some scalar field. So kind of an Einstein-Maxwell Klein-Gordon type system, and this is true for linear perturbations. One could assume that this is true for nonlinear perturbations, but this is far from clear. The linear perturbations of 4D asymptotically flat spacetimes look very much differently than the nonlinear perturbations of the theory, and we really want to be able to talk about, for example, mergers of black holes or what have you in this theory when we have compact extra dimensions. So we really can't rely too heavily on the linear analysis. And for an arbitrary internal space, this compact extra dimension, there exists no local non-perturbative definition of the graviton, graviphoton, or the dilaton. The reason for this is the same reason why there's no local definition of gravitational radiation in asymptotically flat spacetimes. It's only defined at null infinity in this kind of regime where we've in the limit as we've gone to null infinity. There's some notable exception, which is it's not that you can define radiation when you have the internal space or this compact space be a torus, but you can decompose the full metric into Einstein-Maxwell dilaton when your internal space is a very high degree of symmetry, this torus. I can talk about that in more detail if anyone wants me to, but in general, we don't want to make any assumption about the internal space. I want to allow a string theorist or anyone else to be able to come to me and supply me a compact extra dimension. I don't want to, in particular, a priori choose one. So we make no assumption about the internal space, its size, or any of the local symmetries of the metric. We're only going to be interested in the asymptotic behavior, and we're going to make no other assumptions. Okay. So what do we mean by an isolated system? Well, we want to generally characterize the following notion. We want to have an asymptotically flat spacetime, this R4, and we want to fiber over it some compact Riemannian manifold, which we're going to call the internal space. So this, of course, is leading to the theory of fiber bundles. I'm not going to go into too much detail about this. It's not really so essential to understand the basic points of what I'm going to make. So we have some full manifold M, this projection operator pi just maps me from the full space to the base space, R4, and these capital indices represent a tensor on the full space, so this is my metric on the full space. And we're going to require that in the limit as I go to null infinity in the R4, which is the only, that's where infinity lives, every other direction is compact, the full metric asymptotes to the following metric, which is the Minkowski metric plus this internal space metric where S is the Riemannian metric on the internal space. These asymptotic coordinates, mu corresponds to tensor components on the base space, and lower case Latin indices correspond to tensors on the internal space. And so we have these asymptotic coordinate splittings between x, mu, and y, and it follows from the Einstein equations that the Ricci tensor of S must vanish. So we're looking for Ricci flat S's. So this is a prescription. So I prescribe an S basically to define the asymptotics. And so where does this asymptotic condition come from? Well, these asymptotics are consistent with all known asymptotics of gravitational instantons. So if you take, for example, what's known as the Lorentzian ALF spacetime, well, one notable example is this Kaluza-Klein monopole, which is just you take any gravitational lump of any sort with these compact extra dimensions and then go off to null infinity, one finds that these isolated systems in any orthonormal frame have these asymptotics as I go to infinity. So what I'm going to do is define my space-time to have these asymptotics and then ask, how does radiation behave? So I'm going to require that the metric asymptotically obey this condition, but then I'm going to allow it to just satisfy the Einstein equations in the bulk without any other restriction. And it's useful, again, to draw these null cones. Scry here is now the R cross the 2 sphere, but now we have this internal space. And so if I want to draw this internal space, I would, if I take a cross section, which is some 2 sphere, a cross section now also includes this internal space, which I've represented by a circle, but in general, it's some arbitrary compact internal space. Okay, so one can ask questions like, what are the asymptotic symmetries of the space-time? Well, what are the diffeomorphisms that preserve this cone structure? And it's enhanced by the presence of these compact extra dimensions. So one would guess, like Bondi, Messer, and Sachs did, that the asymptotic symmetry group is just the symmetries of the background metric, this eta plus S, where we have the Poincare group, and then which is summed with the isometry group of the internal space. So the isometry group of S of this internal metric S, whose generators we're going to denote as these Vn. So these are generators of the internal isometry. These are just isometries of the internal space. Good. So what we find is that the isometry group is not this. Well, of course, it's not the Poincare group. It should be really BMS here, but it's also not just these internal isometries. What one finds is that the full isometry group is the BMS group semi-direct product with this group Gothic C here, which is we call the group of super internal isometries. These generators are given by here, they're given by these internal isometries multiplied by an arbitrary function of angles. If it's a constant, it's just the usual internal isometry, but for any higher harmonic, it's a super internal isometry. And these are angle-dependent internal isometries. What do I mean by that? Well, if we go to our picture here, you can see the action of a BMS translation as well as a super internal isometry, sorry, a BMS super translation. The BMS super translation just acts on the base space at Scry and then moves my 2 sphere to a wiggly 2 sphere. And the internal isometry is an angle dependent. In this case, it's the internal space is a circle, so it's an angle dependent internal rotation of the internal space. So you can see, depending on where I am on the sphere, I get rotated by a different amount. If S is a constant, the generator turns out, the charge associated to this turns out to be the asymptotic charge of the space-time. But in the higher harmonics, we'll see that it's related to the memory effect as well. Okay, so these are physical things that cannot be ignored in the space-time. Okay, so to understand how gravitational radiation acts in these spacetimes, it's, as I was saying that we shouldn't really trust linear perturbations, but let's just look at how massless linear perturbations, behave in this, background metric, and we're just going to take our background metric to be this asymptotic metric, so this eta plus S, and we're just going to perturb off of this background metric. So it's useful to choose this gauge here. So just within the slide, I'm choosing a gauge. Nothing I'll be saying is gauge dependent at all. So we're just going to choose this gauge to get started and understand how massless modes propagate. So we're going to choose what's called the transverse traceless gauge. It's very clear. It's divergence of H is vanishing and its trace vanishes. If one chooses this, then, for example, the R4 components obey a wave equation, where the box eta is the wave operator on the flats, on this Minkowski space, and then we get this d squared h acting on the metric, where d squared is the Laplacian on the internal space. Okay, so we can easily see that if d squared is 0, then h mu nu satisfies a massless wave equation. And therefore, we've identified the massless modes. They're the ones for which, is annihilated by the Laplacian, or otherwise is just, otherwise stated is just independent of the internal coordinate. We can also do so for the one leg in the internal space and one leg in the R4, and we requiring that this satisfies, a massless wave equation is equivalent to this condition, where it's annihilated by the Laplacian. That turns out to give the following condition, where h mu m is basically given as some sum over isometries over the internal space, where these coefficients of the sum, a mu, have the natural interpretation of a vector potential and satisfy the massless wave equation. These a mu coefficients all satisfy the massless wave equation. And finally, the last equation, it's a bit more complicated. If we require that this is satisfied, the internal components are satisfied. And so solving this equation is not so trivial. One must do this on a case-by-case basis. But if we show that whenever one has a solution, it's generically of this form, where these coefficients phi and these capital phi's here are all satisfy a wave equation. And this bar denotes, a zero mode. So the bars here denote take the zero mode, or basically forget the internal coordinate for both of these quantities. So this is not so important. Basically, one can, all perturbations, massless perturbations, turn into a graviton, a graviphoton, and a collection of scalars. And I've assumed that one has at least solved for a given S and internal space, one has at least solved the scalar equation. So they can, at least in the linear theory, supply me these scalar fields. Okay, and if one has done that, then we can move on to the following, which is how does one do this in full nonlinear, non-perturbative theory, but at scry. So there, again, there's no local distinction of the graviton, graviphoton, or scalar radiation. And it's useful to note, well, how does one, talk about gravitational radiation? One invents this news tensor, which is this capital NAB, capital, indices here correspond to tensors on the asymptotic sphere of this scry. And this news tensor here is gauge invariant, and its square denotes the power radiated due to gravitational radiation. Okay. So can one invent a similar quantity at scry? And so we prove that there exists an analogous tensor at scry, but now scry is, has this internal space whose components satisfy the exact same equations that we found for this massless linear perturbation. But now this is in full nonlinear general relativity. And the fact that it's Einstein's equations is not so really relevant for this point. So this non-linearly and non-perturbatively defines the graviton, the graviphoton, and the collection of scalars at null infinity, these set of equations, in the same way that the previous equations define those quantities in the linear theory. Furthermore, one can show that the sum of the squares of these quantities denotes the power per unit angle of gravitational radiation. So really, these quantities do generate mass loss in the space-time, and really have the status of denoting the gauge invariant gravitational degrees of freedom of the theory. Okay, so this brings me to my last slide, which is good because it's 1 o'clock. The memory. So now, what can one do with all of this information? Well, obviously, if I have a gauge invariant decomposition of gravitational radiation at null infinity, then this will yield a gauge invariant decomposition of the memory tensor into delta AB. This is the gravitational memory effect. This will be the electromagnetic memory effect, and this will be the corresponding scalar memory effect they have analogous properties in electromagnetic theory and scalar theory. Okay, so just as an application of what one can do with this formalism, well, now let's take the approximation where the compact extra dimension is very small. So what are these tensors saying? Well, they're telling you how do the LIGO arms of the detector move in response to gravitational radiation. This is telling you how it moves in the R4. This is telling you how it moves. These two quantities are telling you how they move into the internal space. But if it's small, delta AM and delta MN are going to be undetectable. And delta AB is going to be the only detectable quantity that LIGO could measure. Furthermore, the electromagnetic and scalar radiation, these n's here, which are the time derivatives of the fluctuations of the internal space, will not necessarily be small. And therefore, what one finds is we can prove the following equation, that for LIGO, the memory tensor satisfies this equation here. And I've highlighted the two terms that LIGO could actually measure. Well, of course, LIGO can measure the memory effect. That's the permanent separation of their arms of their detector. And NAB turns out to be the rate of change of these arms of these detectors. And of course, is also measurable due to any LIGO signal, or I should say LISA can measure this quantity, but LIGO is of course measuring this quantity. Anyway, of course, this formula, so in asymptotically flat spacetimes, this formula should equal each other. The nu squared that LIGO detects would be equal to the memory effect that they detect. But as we've proven, the memory effect will be enhanced by the fluctuations of the electromagnetic field, the effective electromagnetic field, and the effective scalar field radiation that one gets out to null infinity, and these quantities will not match. And these quantities can be as large, potentially, as this quantity. And so this is an example of a directly detectable way of that LIGO or LISA could detect the memory effect. Okay, so again, there's no local definition of the graviton, graviphoton, and scalar modes in any full nonlinear theory with compact extra dimensions, but we can give a precise gauge invariant notion at Scry, and we make no assumption of the metric besides our asymptotics, and the presence of these compact extra dimensions is in principle measurable by LIGO or LISA. Our analysis applies to Einstein gravity, but we also investigate the implications of alpha prime corrections. And now we can really do what Ashtekar did at null infinity, but in the context of compact dimensions by non-perturbatively quantizing gravitational radiation at Scry and asking the same questions as I posed in part one, but now within a dynamical theory of quantum gravity. Okay, so I think I'll conclude there. Maybe I will stop the recording, or maybe I'll continue if people have questions, I guess, and then I'll stop it after.
I was just wondering if I could ask a clarification regarding, you're talking about entanglement between the soft and hard modes.
Yeah.
Is that, so you have some direct sum and then you just somehow you partition? I mean, I guess I'm just more familiar with partitioning with respect to a direct product or tensor product structure Hilbert space, but this would be like splitting into one part of the sum and the other part of the sum.
Yeah, so the Hilbert space is for any given memory sector is a direct product, but then you want to put all of these memory sectors together so you can either integrate them via this direct integral approach or take a direct sum. So for every
so you're still partitioning within each memory sector. Right. Got it.
But of course, when I integrate these memory sectors together, now I can have entanglement between different memory sectors because I'm, they're not a trivial direct, they're not a trivial tensor product anymore.
Right. So there's both. It's both interesting to think about. It's both interesting to think about the entanglement between the hard and soft sectors, and then also the different memory sectors. Yes, those are just two different directions.
And both, the measure plays a role in both. That's the key point.
Right. Yeah. Thanks.
Yeah.
How large is the subleading correction to the memory effect compared to the corrections you discussed, like the scalar memory effect and others? Because
you mean in the compact dimension story? How large is it?
Yeah, because I remember the subleading like spin memory corresponds to like a super rotation operations.
So the subleading effects, as you might imagine, are suppressed significantly relative to the leading order effect. So gravitational radiation falls off at order 1/r roughly in some gauge. The subleading effects, so memory is at that order in 1 over R. The subleading effects are at subleading order, right, in 1 over R, and therefore are significantly, since they fall off faster, they're significantly less easy to detect. And I think that it is still currently not clear whether or not the spin memory effect, for example, makes much sense in the context of an actual measurable property of the theory. So I think in full nonlinear general relativity, there's been some linear analysis done, but in the full nonlinear theory, I think it's not so clear that all these proposals to construct or to measure spin memory have concluded that one could do so. So I would have more hope for the true memory effect than for the spin memory effect, just for the fact that it's at leading order in 1 over R.
Another question is when you discuss the Gaussian measure,
yeah.
You impose the 2 conditions. One is finiteness, the other is Lorentz invariance.
Yeah, so the unitary implementation of translations and the boosts, imply constraints on the measure. That's right.
Yeah, does it include the entire BMS group or just the Lorentz group?
Yeah, so what I meant by translations, I meant full super translations. So that meant all of the super translations. And then by Lorentz invariance or Lorentz implementation of the Lorentz group, I meant the full Lorentz group. So by that, I mean the full BMS group I'm trying to implement, but you can kind of partition it into implementation of the translation group, the super translation group, and the Lorentz group.
Not the super rotations that people are discussing?
No. So the super rotations at the level of an asymptotic symmetry don't make any sense because super rotations require one to admit very singular vector fields into the, basically you're just only requiring that the asymptotic symmetry group, you're allowing for conformal killing vectors basically on the asymptotic sphere. And those can also be very singular. And if you allow for such singular transformations of the spacetime, then you can show that the group ceases to be a group, have this group structure. I don't think that that's actually very well known in the literature, but it's been said by a few authors. There's a paper by Aina Flanagan and Kartik Prabhu. I think that emphasizes this point. So I'm not including this because I don't want to include super rotations into my asymptotic symmetry group.
Okay, thank you.